So in this chapter, we're going to investigate what op-amps are. Op-amps is short for operational amplifiers, which is a chip that we use in electrical engineering to take a signal and to be able to amplify it. And we can also do some interesting math because it's not just an amplifier, it's an operational amplifier. So in this chapter, we're going to look at what they are, how to use them, and some projects that we can put them in, and also some of the reasons that they work and some of the logic behind them. And also, of course, the calculations and mathematics to be able to properly calculate gain and other attributes that are important. So let's get started. So here we have the 741 operational amplifier IC, integrated controller, integrated chip. So what we have is a chip here, this black thing on the side and the left and the top. That's the black package. It's a plastic package. They call it a DIP package, um, dual inline package. Sometimes a DIL package, dual inline is also used, but more commonly it's DIP or PDIP, plastic dual inline package, because that black is plastic. The parts that come off of that, the individual legs that are silver there, are the connectors or the connection legs. And these, for DIP packages, DIL packages, and PDIP packages, are designed to fit perfectly into your breadboard, so it makes them very, very easy to use. There's a whole bunch of other different types of packages, SOIC, um, QDIP, a whole bunch of other ones, but for what we're trying to do in lab, we're always going to try to use the DIL, DIP, or PDIP packages just because they're a little easier to handle and they're a little more robust and they plug in nicely. They also have some good thermal properties too. The reason we don't use them in as much in industry is because they're bigger, and usually saving space and real estate on the board is pretty important. So in industry, they'll use these for testing and prototyping, usually, and then switch down to a smaller chip later on to be able to do actual development. So on this slide, we have the 741, which is one version of the op-amp. I believe, yeah, this is one version of the op-amp. And in the center here, we have a brief schematic of how this op-amp looks inside. So this is a symbol representation. We'll look at what the transistor and actual circuits happening inside the op-amp are later. But if you look at, we have a couple different pin numbers here. The pins are numbered 1 through 8 because there's 8 different pins coming out of this op-amp. And we have the ones that are most important to us are the inverting input, which is 2, the non-inverting input, which is 3, V minus, V plus, and the output. Pin 1, 5, and 8 aren't really used as much. We can get into that later in a more advanced lab, but for the initial introduction, we're going to look at just those, 2, 4, 5 pins. So if you look, this symbol with the triangle in it, with the positive, the negative, that is the symbol for the op-amp. And those 5 wires coming out of it, one from the positive, one from the negative, one from the top, which is V positive or power positive, and one from the bottom, V minus or power negative, and then the output. So what the op-amp does is it takes the 2 individual inputs. So you're looking at whatever's coming in the negative and whatever's coming in the positive, and you're trying to figure out and compare those two. And there's other circuits and additional resistors and capacitors and whatnot that we can put into this op-amp to be able to change how we compare them and what the range of comparison is and how we amplify that up, how much we amplify. The green and the red wire here are signifying power. So the op-amp is kind of like you can think of it almost like a normal electrical device that you plug into your wall. It needs power in order to function. It needs its own set of power. So you can think of that red wire and that green wire in this drawing as the 2 wires that you plug into your wall. A little different though because it allows for V positive and V negative, and your wall has a ground and a positive. So it's slightly different. You can attach, in some situations, the green wire to ground and the red wire to whatever your power supply is and make the op-amp work that way. But we'll talk mathematically why sometimes that isn't the most optimal way of doing op-amps. So here we have another op-amp. This is a dual op-amp. It's a TL072CP. And if you type that into Google, you can find a data sheet for it. So a lot of op-amps have, nowadays, have multiple op-amps inside just to save space. So that's what this chip is doing. This is saying it has 2 different op-amps inside, and they're both sharing the same VCC positive and VCC negative. So both of these chips are going to share the same power supply, and essentially that saves two individual pins. And if you notice, you don't have the offsets of the previous slide, and you also don't have that not connected pin. So all the pins here do something. So if you look on the left-hand side, that's written out which pin number does what, and you can always tell that you're in the right direction by that little circular piece in the middle on the top, that little indent. That allows you to orient your IC so you face that side facing you, so the legs of the IC stick towards the back, and that little pinpoint, that little circle dip concave sticks straight up, and that way you're always oriented the same way every time, and you can't mess that part up. So on the right-hand side, we have the internal representation of the circuitry showing two totally separate op amps. And again, they're just sharing that same power supply. So it's like two of the previous op amps on the previous slide combined into one chip. We also get something, this is the MCP6004 quad op amp. And these are great op amps. We have a lot of them in lab, actually a couple hundred right now, so they're a good chip to use for different types of projects. But the MCP6004 is by Microchip, and this is a quad op amp. So this actually has four separate op amps inside of it, and they all share the same VDD and VSS, so voltage positive and voltage negative. And again, you can always set one of those to be the negative one to be ground if you're just trying to amplify to the positive half. But these op amps, again, since they share the same voltage, though you can't have different top peak voltages. It is the same peak voltages across all four. Uh, so again, we have up here it says three different types of electronics packaging: PDIP, which is plastic dual inline package, SOIC, and TSSOP. So SOIC and TSSOP are surface mount components, and therefore we try to avoid those in lab because they're much smaller and they're much harder to solder in, and you need to solder them to a board for them to work. They won't plug into a breadboard. So PDIP are the ones like the picture on the left shows with the legs that plug nicely into your breadboard. So if you're ever ordering for this project or any deck projects or whatnot, electrical components, you want to look for the PDIP, the DIP, or variations of that. The SOIC, TSSOP are for finished prototypes, finished products. So again, we're going to review through ICs or integrated circuits. That's what that packaging on the right is. That's essentially saying that there's more going on to this component than just a resistor or a capacitor. There's a whole bunch of interior electronics that are packaged nicely so that they do something very specific. So 8-pin means that there's 8 pins sticking out, 8 different legs on the integrated circuit, and that's what we see with those silver lines on the right in the picture. DIP, which is dual inline package, which is the type of package that holds those interior electronics. The goal for the dual inline package is that it plugs into the breadboard. So for different chips, you're going to have different voltage thresholds. For this particular chip, which it says what? It's the 741. You can read that on the very top of the package. That's going to say, the data sheet's going to say what the top voltage is going to be. So the 741 can take up to positive 12 volts and down to minus 12. If you go back previously to the quad op amps, the MCP6004s, those, if I remember right, go plus or minus 6 volts. And you're going to want to check that. I'm pretty sure it's 6 volts, though. So if you try to plug one of those quad op amps into a 12-volt power supply, you're probably going to burn it out real fast. Likewise, if you plug a 6-volt power supply into one of these 741s, you're not going to be optimally using the op amp. It'll work, but you'll have a smaller range of values that you can play with. So again, what else do we have for this one? We have input signals on 2 or 3, which is the inverting and non-inverting inputs, and we're going to look at what that means in a minute. And then your output from whatever your circuit is comes out at pin 6. And in this diagram, if you look at the right, you have a little dot in the top left corner. That's another way that some chips have to make sure you're oriented properly, so that dot faces up and to the left. And op amps are kind of cool because previous to the 1950s, they were over $100 a single piece. And now 89 cents at Radio Shack is even expensive. You can get them now for 25, 30 cents if you buy them in bulk for different electronics projects. So they're very robust chips. It's as long as you follow the data sheet, it's really hard to break them. They last for a while. You don't have to worry if you're in like in space or whatnot. You don't have to worry so much about radiation because usually the transistors they use inside of them are pretty well pretty well done, pretty robust. So let's continue on with op amps. What op amps are not used for? So op amps are not they can't deliver any significant power. So remember I said previously we plug op amps into a power supply to power them. They're not like a voltage source or a current source. They don't mathematically work that way. They're sucking power out. And op amps actually will get a little bit warm when you use them because they're like a resistor. You lose power by using them. They take some of the power out. So they don't deliver significant power. And on top of that, the current that comes out of an op amp is usually around 10 milliamps at 12 volts, so 120 milliwatts. So for certain op amps, and this depends again on the data sheet, some op amps can't even power up an LED and make that turn on and off. That's just how low. And the LEDs we have in lab right now are 20 milliamps forward current. So with that in mind, you got to kind of watch what your application is to make sure that your data sheet and you select the data sheet confirms that you've selected the right op amp for the job. So some op amps have a much higher current output, but still the current output's never enough that you could drive a motor or a speaker or other things. You want to have a different circuit after that, and we'll talk about what those circuits are. But the op amp is more of a mathematical amplifier, and if you want after your amplification to drive something or do something with that, you have to have some type of alternate circuitry in order to power your motor or your uh, LED lights or something bigger than that even. But for the mathematical part, they're really great at boosting up a small signal and making it bigger. So this picture is the 741 op amp inside of it. So if you took one of these plastic packages and you cut it open very carefully, on the top left, you'll see what you'll see. There's a little tiny square in the inside of it, which is about the size of a head of a pin, and it's mounted using thermal paste. And there's a bunch of these wire bonds that are soldered very tightly to this tiny little chip that fits on the head of a pin or a needle. So these wires are extremely delicate wires, very small, and this is essentially the chip. So of that big black package, 80% of it is just empty space. Um, that 20% or even less, sometimes it's 1 or 2%, is where your functioning electronics are. So they make these really tiny. They just make them bigger into that black package so that you and I can handle them and work with them more predictably. So if you look inside of here on this diagram, you'll see inside of the op amp what's actually happening. And the symbol, you'll see a whole bunch of transistors here. Those are usually denoted by the call out Q. We have a whole bunch of resistors internal inside of the op amp, which are usually call outs by R, but here they just give the values. And I think you'll see a couple capacitors in there as well. Yeah, I see one. Yeah, there's a couple capacitors in there, and those work internally to provide some smoothing to the signal and some other parts. But we're not going to go into this level of calculation for the op amps. We're going to look at op amps essentially as little black boxes. So we know that they have defined properties given by their datasheet, and we know that whatever we input is going to be output based upon that datasheet and those defined properties. And that way we can skip calculating every single transistor in this, because you can do that. Every transistor here can be calculated out, and you can start to look at all the different properties that you need to actually build an op amp. But there's no reason for that. It's a lot of wasted effort because usually we'll just use the entire chip as it's packaged and comes from the company. Because calculating this out will take 1 or 2 hours if you're good but it's not worth it. So we're going to skip that entire section, and we're going to call in op amps as black boxes. So we give them a set of inputs, they follow a set of rules, and they give us a set of outputs. So again, we have inside of here in the schematic diagram, we have the non-inverting input, which in this diagram for the 741 is coming off coming into the transistor Q1 and the not and the inverting coming into transistor Q2. And you can also see where you're pulling the outputs from as well. So you can use this schematic to actually build a 741 out of transistors and resistors. But again, for 50 cents, you can buy one of these pre-built. So I would always, in that regard, buy the pre-built and save yourself some time. So what are op amps used for? So op amps are probably the primary piece of electrical equipment we use right now in the construction of simple and complex signal processing. So you can do mathematical functions with op amps, and that's really where their value is. The amplifier value is pretty cool too. In order to take a signal and make it louder, take something, a very small signal coming from like an iPod or your cell phone headphone jack, and then boost it up to something that you can listen to on a 40-watt stereo system. Op amps have a part to play in that. However, they also have a lot more because you can do mathematical functions with them. Amplifying, which is essentially just uh, multiplying a given function, an input function, by some value to make it louder. So that's what this mathematics, the mathematics here is saying about the amplify or attenuation. You have a y of t, and that is your output, and that equals g, which is your gain, times a of t, which is your input. So it's just saying that you're taking your whatever your input signal is, you're multiplying it by some value to make it bigger, and that's where your output is. So that's what the amplifier circuit is. They're the most basic. Buffer are also pretty basic circuits. So buffer circuits, essentially you're saying your input equals your output. So buffer circuits are really important because they can protect electronics. They don't give any gain, so you're not getting any louder when you use a buffer circuit. However, you are preventing damage from happening to electronics, so you use them kind of to protect more sensitive electronics along the way. We can look more into that in class because there's a couple really cool examples for that. And I think a couple diagrams you'll understand a little better. Next, we have the inverting op amp. So the inverting op amp is like a buffer op amp, except it flips the signal. And so signals can flip because mathematically, and you do that to get some special features out of it. So, for instance, if you have noise canceling headphones, like by Bose or whatnot, are actually sending to your ear the exact opposite signal that is coming into the little microphone on the outside of them. And so they listen to that and they send the exact opposite signal, and 1 plus -1 equals 0. So essentially they cancel out the noise before it hits your ear, and that's how you get complete silence that you get with those. And there's a whole bunch of other signal processing and filtering electronics that go with that. However, that's the basic principle of inversion. So it's a mathematical way of flipping your signal exactly opposite so that you can do something with it or cancel it out or whatnot. We can subtract signals and we can add signals. So that's saying if I have a signal of if I have a signal of a bird chirping, so it's a sound, and I have a really noisy highway with the constant drone of like trucks going by. Those are two different signals. And so let's just say I wanted to just listen to the bird. Op amps provide a way, in a sense, of being able to subtract out the trucks and just have the birds. And so it's a little bit more complicated than that, especially since trucks have different frequencies and there's a lot more going on. But essentially, it allows you to remove one signal from another signal for either cleaning purposes, or you can put one signal back. So adding signals is what DJs use when they try to mix two songs together, and you have one song playing and it fades into another song. Essentially, you're adding the two signals together, the two different songs, uh, based upon different proportions. So maybe you fade in, so you have 90% of one song and 10% of another, and as you tune it up, it's 50-50, and finally it's 10% the old song and 90% the new song. And so that's how you can add signals, and op amps allow you to do that as well. Finally, you get into the really interesting parts where you're taking derivatives of a signal, and you can integrate signals, and you can build active filters. There's a whole bunch of different mathematical operations that you can do. So the most interesting part to me, and I think a lot of people in analog electronics that work on these, is you can actually solve differential equations with op amps. So op-amps can actually be used in a very esoteric way to solve very complex computer problems the same way that a graphing calculator can. And so early on in space in the space race and in spacecraft engineering, they would use a lot of analog computers to solve problems, complex problems, very quickly. And analog computers do have a small advantage over digital computers, and that's that they function and they can calculate extremely quickly, whereas normal computers can take a bit longer to calculate out because they're running a lot of other processes. Analog computers are almost immediate in the amount of time that they can output an answer. So that can be useful when you need something that has extremely fast response time. So um, Boston Dynamics has done a whole bunch of different robots like Big Dog and whatnot, where they require their robots to have extremely fast sensitivities and extremely fast response times to be able to navigate some type of external variable, like somebody kicking on one of their robots or wind pushing on it or something like that. And analog computing has a part to play in being able to process that data very quickly and very effectively so that the response time to these is maintained. That also goes with a whole set of controls engineering, which we'll get to eventually in systems and controls. So like I said before, there's a whole bunch of different types of op amps. Here are a few of the most used ones. So at the top we have a non-inverting amplifier. A non-inverting amplifier means whatever signal is coming in, we're going to make it louder and we're going to spit it out of the chip. So as whatever that signal is, we're not going to do anything else to it. We're just going to make it louder. We're going to make the amplitude higher. And so we make the amplitude higher by something called gain, and that's G. And this green box here shows the equation that we use and to make that gain, and that goes with the configuration of resistors on the right. So the exact resistors don't really matter. It's the relationship between the resistors. The relationship between R1 and 2 and 2 allows for us to change the gain of this non-inverting amp. So this is the same kind of, a non-inverting amp is the same kind of amplifier that you use to take your iPod and boost it up to be able to play some speakers or something. That's what a non-inverting amplifier does. Similarly, below is the inverting amplifier, and you'll look, the signal diagram is almost identical to the non-inverting, except the signal goes in, the plus and the minus in the triangle, in the red triangle is flipped. And an inverting amp does the exact same thing as a non-inverting. It makes the signal larger by a function of g, but it also flips it upside down. So whenever your signal or your waveform goes up in the top one, it now goes down in the inverting. And this can be useful for noise canceling. This can be useful for mathematics. It essentially functions as almost like a negative sometimes. So your inverting amp is another tool in your arsenal for op amps to be able to generate more complex calculations. Under that, we have the inverting summing amp, and then similarly, if you flip the positive and negative there, you can have the non-inverting summing amp. But what this does is this takes three different signals, V1, V2, V3, and it plays and overlaps them all together. So this is the kind of setup that a DJ would use to be able to control three different songs playing at once. So three different sounds or tracks, or maybe a drum on your V1, and maybe something else on V2 into V3. So this adds them all together, and that's all it does. Your gain is determined, and your amplification, because it is still an amplifier, is determined by the relationship of R1, R2, and R3 to RF. And the equations in green here will let you calculate your gain. So you can set the summing, inverting and non-inverting summing amplifiers up to have 90% the volume of the first song, 5% the volume of the second song, and 5% the volume of the third song. And that's essentially coming out to V0, which is your output. So you can tune them based upon the relationships of the resistors R1, R2, R3 to RF. Similar thing with the subtracting amplifier. So the subtracting amplifier, like I said before, is taking like a noisy signal and removing the noise to have a cleaner signal. And we use this one a lot in biomedical. So if you're taking heart readings, which are very, very electrocardiogram readings. They're very, very small readings, and it's very hard to get a signal from the heart. Not as hard as getting signal from the brain for an electroencephalogram. However, hearts are still pretty hard to get a signal from compared to other types of signal generators. So with that, whenever you take a signal from the heart, you also have to take a signal from like everything else that's happening. So if you're sitting in your room, your electrical wires are going to produce a hum at about 60 hertz because that's what AC power is, the frequency of AC power. Plus, if you have LEDs in the light in the room, a lot of LED light bulbs have their own frequency. And so to step back, there's a story I have when I was at Philips. We were doing testing with MRIs, and MRIs have very, very sensitive magnetic fields. And so essentially any little electromagnetic noise comes out and can be seen clearly in an MRI. And we were using an MRI on a Friday, and we went in to use that same exact MRI on a Monday, and nobody had touched it in between when we used it. And we tried and we couldn't get it to work and we couldn't get any signal out of it. And we were trying to diagnose for the entire morning of how we lost signal and how the signal was so bad. And it turns out over the weekend the janitor had replaced one of the light bulbs with an LED light bulb. And the LED light bulb has a frequency because it flickers on and off. And that was enough to mess up our MRI readings. And so you're able to do two things. In that case, you could remove the light bulb and put a normal one in, which is what we did because it's the fastest. Or you can calculate out what the frequency and noise of the light bulb is and subtract that from your MRI image. And essentially, that's what the subtracting amp is doing. You're taking a noisy signal and you're subtracting the noise out so you get a cleaner signal. Underneath that, we have the voltage follower or buffer, which is, again, one of my favorite circuits because it's very simple. And essentially what it is you're just taking some of the output and you're tying it to your input. And this has an amplification level of 1, so it's not amplifying anything. So if you have a signal that's 1 volt coming in, you'll have a signal that's 1 volt coming out. Why this is important, though? Because this can protect electronics. We're going to look at ways to calculate op amps, but you'll see that actually no current flows in and out of that plus and minus sign on the op amp. And because no current flows in and out of it, essentially you have a really nice way of protecting something before the op amp to something afterwards. In case you have a spare shock or a charge or something goes wrong, a buffer circuit can really be a hand in protecting your more sensitive and expensive electronics. After that, we have a non-inverting summing amplifier. So this is similar to the inverting summing amplifier. If you look at it, they're very similar in both the ways that you calculate them and in their setup. So that's another one available as well. On the right here, we have, again, one of the dual op amps, so it has two different op amps inside of it. In class, mostly we're going to be using the quad op amps, the 6004s, but just know that there's a whole bunch of different variations from different companies, and they have different numbers, but they're all kind of doing the same thing, and they all follow the same rules that are shown on this page, unless otherwise noted in the data sheet. So here we have another video, another display of an op amp or operational amplifier. We've got two input terminals, positive, which is the non-inverting, and negative, which is the inverting. We have one output, and then we have a power supply VCC and minus VCC, or VDD, or positive V and minus V, depends on the write-up. Underneath, you can see an op amp showing a power supply. We have, in this op amp in the bottom left, number 3 is the non-inverting input because it's going into the positive. We have the number 2, which is the inverting input, and that's coming in and inverting because it's the negative. We have our positive power supply at 7 and our negative power supply at 4. And you'll see there's two power supplies there. One, they're flipped, the positions, in order to create the negative and the positive power supply. 4 sometimes in some op amps can be tied directly to ground. You want to check your configuration out, though, to see that that makes logical sense and mathematical sense as well. And then finally, you have pin number 6, and 6 is your output. I0 is your current out coming from the op amp. And op amps can't really put much current out, but they do a good job at amplifying the signal or the voltage coming in. So that's kind of their utility. On the right, we have an op amp with the power supply not shown. So often we're going to just ignore drawing the power supply, and we're going to do something called draw a rail. And that's what that ground line is doing below. It's saying, hey, there's one line here that's ground. The op amp's power supply isn't really that important because you're going to spec it out ahead of time. If your signal that you need is going to be a maximum of 15 volts out, you're going to use an op amp that has at least a 15 positive minus 15 volt power supply, because otherwise you're going to lose some of it. If you try to power an op amp with a 5 volt positive and 5 volt negative power supply and get 15 volts out, it's not going to work. Whatever your power supply is, that's the maximum amount of voltage that op amp can deliver. And again, we're going to look at that a little bit more in the future. So here we have a slide on gain, and I've said this a couple of times. Gain is the number that you multiply by to get your increase in volume or your increase in amplitude. And so op amps have inherent high voltage gain. So in fact, if you connect no supporting electronics to your op amp, your gain is so incredibly high that it's almost unuseful. So in the bottom left, we're going to look at an open loop op amp, which means there's no feedback, there's no resistors coming back into the inverting or non-inverting amplifier. And essentially what this op amp is, it's called a comparator op amp, and it compares between the 2 points. If one is even slightly higher than the other, if the positive is even slightly higher than the negative, then current is going to flow out. So this is kind of, it can be useful, but at the same time, it's usually not, because if it's even ever so slightly, and that could be on the level of millivolts, or even in some op amps down to nanovolts higher, then you could have an output when you don't really want one. So that makes a lot of jitter. So if you're trying to send a rocket into space, and this is on your control, and you're using the comparator to press, like if I press the button, then essentially launch the rocket, you're going to get a lot of false positives in there, and your rocket's going to launch way earlier than when you actually wanted it to launch, and that's dangerous. So sometimes we use comparators, but in general, there's better circuits for that. On the right here, we have the negatives in a diagram showing the negative saturation region and the positive saturation region. In a comparator, there's almost no diagonal in the middle. It flips immediately from negative saturation to positive saturation. In well-designed op-amp circuits, you're trying to essentially tune the slope of this graph so that you lie somewhere within the linear range, because that's essentially the region that's amplified and not saturated. Once you get into the positive or the negative saturation region, you're starting to lose data. You're losing some of the data that you're putting in, because it can't cope with that. So if you tune it properly, all of your op amp input and whatnot, and the saturation and the gain of that op amp falls within that linear range, which is your goal as an electrical engineer. So in this slide, we're looking at what the equivalent circuit for an op amp is. And this is just another way of looking at mathematically what's happening inside of the op amp without going down to the transistor and resistor and capacitor level. So what we have here is we have an equivalent circuit drawn out. We have VP and VN, so voltage positive, voltage negative, so the non-inverting voltage and the inverting voltage. And these are going to come into the op amp, and we have this resistor Ri inside of there, which is essentially the op amp is trying to keep these two inputs, the positive and negative, to match. It wants them to be matching. So this internal resistor is essentially the part that keeps the inputs apart. You can think of it that way. So the input resistance is large usually. The higher the input resistance, the higher this Ri is. Essentially, the better off it is for a signal processing, because if these are the same and there's very little resistance between the two, they're kind of muddy together, and you're not going to get that differentiation between the two different signals, the two different inputs. So Ri in most applications and most op amps is between 10 to the 6 or to 10 to the 13th, so above a million. In reality, in an ideal op amp and in the mathematics that we do, we have infinite resistance in between there. So that's essentially saying that there's no talking back and forth between the VP and VN. There's no current that flows backwards. In reality, there is some current that flows in and out of there, but again, for the mathematics to work, and we only want a broad sense right now before we dig deeper, the broad sense says we want an infinite resistance between there. Likewise, on the output side of the op amp, we have that little red diamond shape, which is the symbol for a dependent voltage source. And we can think of this as a dependent voltage source from ground, so it's boosting up a signal from 0. And we have R0, which R0 we want to be 0 because we want all of the signal to come out of the op amp into whatever our electronics is. We want the maximum output as possible. In all reality, though, the op amp consumes a little bit of power and it's not perfectly efficient. So actually, there is a bit of resistance there, usually between 1 and 100 ohms inside of the op amp coming out. And so we want that to be very, very low, as close to 0 as possible, and better op amps have lower resistance there. Um, Mathematically, though, we presume it's 0. We also have the presumption that the gain is very large, and so the higher the gain, essentially that's saying a better op amp. We presume they have infinite gain um, from the linear input to output response. So that's the open loop gain A, or G, how it's known sometimes. In all reality, it's 10 to the 4 to 10 to the 8 volts to volts, but in our mathematics, we presume that's an infinite gain. And so what other ones that are important on here? Our supply voltage, VCC and minus VCC. This is going to be totally dependent on the chip. And usually the typical range is 5 volts to 24. I've seen a couple that go as low as 4 or 1 for specialty op amps. And I've also seen a couple that go really, really high, up to 48 volts. And those are, again, specialty op amps. And they're also much more expensive, too. But the only way to figure that part out is to read the datasheet of the op amp you're using. So again, the MCP 6004s, which are the quad op amps, which are one of my favorite to play around with because you have 4 of them on there, and you can do a bunch of math without unplugging anything. Those, I believe, are minus 6 to 6 volts. So that's just one thing that you got to read on the datasheet. Anything else with this important one? Yes, so output is proportional to the difference between the two inputs. Again, so it's VP minus VN, so the difference between the non-inverting and the inverting times the gain equals the V out. That's kind of the concept of what the op amp is. So this is our first example slide. This is example 4.1, which is the first example of the chapter, showing an op amp circuit and asking you essentially to calculate out the gain for it. And so they give us the set of values, VCC equals 10, A equals 10 to the 6, RI, R0, R1, R2, and they want us to calculate what the gain is coming out of it. And so first step of doing these is to identify what type of op amp this is. And looking at it, we can see that the signal, which is VS, voltage signal, is coming into the positive side, so that is a non-inverting op amp. And we also have that feedback coming back there as well. So this is a non-inverting op amp. And if you look below, the first bit below is is a calculation V out over Vs. So the gain can be calculated by the voltage coming out divided by the voltage signal. That's essentially what the gain is saying. And we calculate this out in all reality, you're going to get 4.9999. Now, if we perform our normal calculations, KCL, and we can do that at node A and node B, which is shown there, we can put those two equations together and solve for the infinite gain A. So the infinite gain A is the mathematical approximation we make based upon those things we said in the previous slide about infinite internal resistance between VP and VN and absolutely no resistance between the generated signal and the output. And that's going to give us an answer of 5, a gain of 5. And if you look between the two different gains, they're almost exactly. 4.999975 is pretty much 5. So for all intents and purposes in REE class, this simpler calculation holds up perfectly for what we need it to do. And again, all we did for this one is we took KCL at node A and KCL at node B, just like we did in chapter 3, and that's how we are able to arrive at our gain equations here. Or we could use the gain equations from the previous slides showing, hey, this is a non-inverting op amp. We identified it, and now we look at what the gain equations are for a non-inverting op amp. And so that's the ways that we can solve this. On this slide, we have a negative feedback. And so what is feedback? So feedback is saying I'm taking a little bit of the the output coming from the op amp, and I'm taking a small amount of that and feeding it back into the negative or the inverting or non-inverting input. And so what this does is this decreases the input signal. Now, if we had no resistors, so you can see there's a voltage divider between the R1 and R2, and we're taking off some of that voltage in between. If I had no R1 or R1 equals 0, then all of the current from that output, all of that voltage goes back to the negative non-inverting input, and that kind of circuit, again, to pull it full circle, is a buffer circuit, and you're going to get 0 amplification. So that's why we have these R1 and R2. Those are what provide us our amplification, because we're only want a small bit of our output coming back to our as an input. We only want a little bit to feed back. So this is how we can achieve the desired gain. By tuning R1 lower, our gain is going to go lower. By tuning R1 higher, our gain is going to go higher. So if I have R1 equals 0, there's no gain. If I have a signal that is 5 volts coming in, it's going to be 5 volts coming out. Now, if I have an R1 that is 2 ohms and R2 equals 1 ohms, because remember, that's also a relationship. Since R1 is twice what R1 is twice what R2 is, my gain coming through there is going to be 2. So if I have a 5-volt input signal, I'm going to have a 10-volt out. And so that's essentially what feedback is doing. The negative feedback says I'm feeding it into the negative side. No feedback says I'm just essentially comparing the two. And a no feedback op amp is a comparator, and it's kind of a waste of a comparator. There's better circuits to be able to compare things. So we really don't use a no feedback for op amps. We almost always use some type of feedback, whether it's a feedback of 0 for a buffer circuit or a feedback of different resistors to get some type of amplification. So again, there's one other bit too, that if your op amp, that VCC, it says is 10 volts there, we don't always draw them, but if that's only 1 volt powered, you can't go higher than that. Your output at max is going to be 1 volt. So that's just something to keep in mind too. On this slide, we have a trade-off between gain and dynamic range. And again, your book details this pretty well, so I'll go through this quickly. But your dynamic range is essentially your unity gain. That's essentially the amount of range that you have in a unity gain situation. So your gain is 1 in that case. As your gain increases, the slope on your graph also increases. So you can see gain 5 is slightly higher slope, and gain 10 is an even higher slope than that. You want generally to have, for most applications, a modest or high gain. There's also very high gains, which you have to be careful with those because sometimes you get a lot of noise in those. And very low gains, which essentially is the unity gain or the buffer circuit, those don't even have any amplification, so you're going to lose data. So your goal as the electrical engineer is to find that correct slope of the curve and stick within that slope of the curve to amplify whatever your given signal is to a reasonable output that you can later perform a filter or signal processing or whatnot on to be able to clean up the signal. So this is a really fun little circuit. I like this one a lot. This is an op-amp switch. So op-amps can be used as a switch too. And that's what this one is doing. So we've designed this circuit in the top to have a red LED and a green LED and an op amp, and you're going to have two signals, a VP and a VN. And again, if VP is greater than VN, then you're going to have current coming out of the op amp. And if it's in reverse, then essentially what you have is your red and green LED will blink and flash back and forth. So this also takes importance of the properties of LEDs, light-emitting diodes, and the functional part of that is diode. And diodes essentially allow current to flow in one direction and not allow it to flow in the other. So this circuit is making a huge amount of impact based upon that property of the diode part of the LED. If this won't work with normal like light bulbs or incandescent light bulbs or whatnot. It has to be the diode section, or you have to have diodes in it somewhere. But essentially what this is saying, if we look in picture B, if we have 2 volts, a positive 2 volts on your non-inverting pin, suddenly that's going to make voltage flow out of the op amp, and that's going to flow through, it's going to try to flow through both of the resistors, and it's going to try to flow through both the LEDs. It's going to be able to get through the LED because its current is flowing in the direction of that LED is facing, so it's going the proper direction through the LED, and that red LED is going to go on. However, the green LED is going to act like an open circuit, because remember, current can't go and flow opposite through an LED. And because it can't flow opposite, that green LED is going to stay off, and we actually treat it like a short circuit. I mean, an open circuit there, not a short circuit, excuse me. However, interestingly, if we flow minus 2 volts into that non-inverting terminal, we're going to be able to suck power out, and the power is going to go in the reverse direction. And since the power is going in the reverse direction, that's going to make our green LED turn on. And so this is an interesting circuit. Again, you're going to have to calculate, if you want to build something like this, you have to calculate out your resistors to be able to protect your LEDs because you have a 12 volt and a negative 12 volt supply. But this is a really nice way to have an op-amp switch. So if you have positive 2 volts or negative 2 volts coming in, you can turn two LEDs on and off in a semi-analog way. So in this slide, we have a circuit analysis with ideal op-amps. This image in the top left, we've kind of explained before. This is like a comparator circuit because there's no feedback loops. And you also have your rails on the bottom showing that you have a ground that your op-amp attaches to. And we just presume we don't draw it in to save two lines. But the ideal op-amp has a current constraint, IP equals IN equals 0, which means no current is flowing into the positive or negative terminals. There's no current going in or out. We also have a voltage constraint, VP equals VN. And we also have on top of that an infinite gain for the op-amp. So that means we can go as high as we want to amplify it, where in reality we can't go infinitely. We can go very, very high though, tens of powers high. And then we also have an RI, which is the internal resistance of infinity, which is saying there's no power going in and out of the positive, negative terminals. There's no power being shared back and forth between them. No current is flowing. And we also have R0, which is the output resistance. There's no resistance on the output. No power is lost. And these rules for the ideal op-amp are what we base all of our calculations on in this CE class for now. There are way more complicated ways of calculating op-amps out, especially if you're trying to get it down to the absolute thousandth of a percent of error. But for our purposes in class, having a percent of error in an op-amp is totally acceptable because usually the resistors you're going to use have 10 to 20% tolerance anyway, so there's no reason to over-engineer the op-amp half if your resistors aren't going to be great either. So in order to calculate circuits with op-amps, we primarily rely upon nodal analysis, but with these golden rules, and these are always held for op-amp calculations. 1 VP equals VN. That's the first bit. The op-amp, there's no voltage drop across an op-amp input. The next bit that we have is IP equals IN equals 0. There's no current going into the op-amp at the positive or negative terminals. And another one that we have is do not apply KCL at the op-amp output. And we're going to talk why that is in a couple later slides. But these are the basic ideal op-amp rules. Your book describes these pretty well, so I would highly recommend going through your book and reading up on these. But this is the first approach to calculating out op-amp circuits. So rules for solving an ideal op-amp. Though op-amps are more complex circuits, if it's in its ideal state, op-amps can be solved with a few simple rules, and the solutions come out pretty darn accurate, so that's what we're going to do in this class. The voltage at the inverting, negative, and non-inverting positive terminal is always the equal. No current flows into or out of the inverting positive or minus terminals, and the output voltage will change in order to keep rules 1 and 2 true. So essentially the op-amp is always trying to make the inputs equal in voltage and also always trying to make sure that there's no current coming in and out of the op-amp. So in this depiction, we have a non-inverting amplifier. So non-inverting, like we said previously, it's like you can think of a headphone jack amplifier or a sound amplifier. And we have a circuit diagram for that where we have Vs, which is our voltage of our signal or source, but usually I think of S as signal. We have a resistor there to kind of bounce that signal down a little bit just in case it's too high for the op-amp. And then that goes into the non-inverting input. And then if we look at the output, some of that is feeding back into the inverting input, the negative side. And the percentage of it feeding is based upon the relationship between R1 and R2, which that relationship is called the gain and is solved by G equals R1 plus R2 over R2. And so essentially what this op-amp is doing in short is your output equals your gain times your input. And that's essentially what this entire circuit is showing. So if you look at node Vn, again, we don't want to take the KCL directly at the output. We want to go down after the resistor, R1. But if we take that the KCL there, we have Vn minus V0 over R1 plus Vn over R2 equals 0. And that's going to say that Vn equals Vp equals Vs. And we're going to be able to solve for that. And we're going to solve V0, which is V out, equals R1 plus R2 over R2 times Vs, which is the voltage of the signal. And again, if we back solve that down and we want to turn this full circle, we go to the light blue box on the left, and that's the equation for gain. And that's essentially how we find our gain for this. And again, just to reiterate, gain is how much of the amplitude we've increased. So if we make a gain of 1, there's no volume increase on a sound speaker system. If we make a gain of 2, we've increased the amplitude twice. A gain of 3, 3 times. So that's the way that we mathematically can think of it. Inverting amplifier, almost the exact same as the non-inverting, except you're going to get a negative here because you're sending the signal down whenever your input goes up. The amplitude is going to stay the same based upon the gain. And the gain for this circuit is minus RF over RS. And again, you can perform the same KCL analysis. It's included here so that you can kind of review through it. But that same KCL analysis at node Vn is going to give you your op-amp gain, which is minus RF over RS. The minus is important because it's inverting. So again, it's flipping it upside down. So this is essentially taking your number and multiplying it by negative 1 in an equation sense. In this example, we have 4.2, which shows an input current source. So in this case, now we're starting to see some more practical op-amp circuits. If we look in A, you've got a current source in parallel with a resistor. And if you remember way back to chapter, I think it was either 1 or 2, maybe it was 2, we can do a source transformation on this. And we can turn this into a voltage source, which we're going to do every single time because that makes calculating out the op-amp much easier. So you want, if you see a current source and a resistor, you want to couple that together to do a source transformation and change that into a voltage source. And once it's in a voltage source, it becomes very, very easy for us to calculate because this is the same equation that we showed before. Summing amplifiers are interesting because it allows you to add two different signals together in different percentages. So you can add 50% of one signal and 50 of another. You can have 75% output of the output is from signal 1 and 25 from signal 2. So essentially, it allows you to pick and tune which percentages you're adding. So usually with summing amplifiers, the R1 and R2 are going to be potentiometers that you can tune and turn up and down. And that's going to allow you, in a music sense, to be able to fade from one song to another song. Signal 1 to signal 2, V1 to V2, source 1 to source 2. And so by tuning these, you can turn and tune the song up and down and fade evenly from one to another. So if we have this original circuit on the top with two different sources and two different resistors, we can do a source transformation to pull, again, a current source in line with a resistor and a current source in line with a resistor. And then if we remember, current sources in parallel can add together, and resistors in parallel can add together. And so we can reduce that one more time to a single voltage and a single resistor. And this is like the Norton and Theravin circuits that we did before. You want to take these more complex circuits and combine them to make them even easier. So while the top one in figure A is a summing amplifier, the bottom one has already shown the signal summed together. And we can do essentially a mathematical analysis of this to show that the two different inputs are multiplied by the two different gains, and then that all comes together as a single output. So that's what the bottom right is saying. V0, which is the output, equals the gain of 1 times the first signal plus the gain of 2 times the second signal. And this is an easier way to be able to calculate these out sometimes than the initial one at the top. So in signal example 4.3 here, we have our first equation. So it would be regular to say to get just the part above the blue line and develop the bottom part ourselves. So the given example is design a circuit that performs this operation. And we're given an equation, V0, which is the output, equals 4 times V1, 4 times the first signal, plus 7 times the second signal. So essentially what we have here is, because we have a plus there, that to me says summing amplifier. And then the 4 and the 7 are the two different gains. So the first thing I do is draw a summing amplifier down in stage 1. And these two different gains in this particular example are both going into the negative, so it's inverting them. We don't want an inverting. We don't want -4 plus -7. We want a +4 plus +7. So we do, at the very last bit, a inverting op amp to be able to flip that signal back to the positive. And we make the numbers for that inverting op amp 1 and 1. So it's a little silly to use both op amps. I would have taken both the signals from the beginning and plugged them both into the positive non-inverting side of the op amp, and that way I could have had one single op amp for this process. But this example shows how you can essentially add multiple op amps together to get equations, and much, much more complex equations. So you can go through this one and solve it. The book has a really good description as well, and some worked out solutions. So in this slide, we're going to look at the difference amplifier, which we started talking about before. And the difference amplifier, or the subtractive amplifier, is essentially allows you to subtract one signal from another. And usually it's used to subtract, to take a noisy signal with something good in it and subtract the bad noise out just to get the good. That's the usual situation that a difference amplifier is used. But there's a couple other more esoteric situations as well. So here we have the circuit for an op amp, a differential op amp or difference op amp. And this is, you see two different signals, V1 and V2. And essentially what this is doing is taking some of each of those signals and feeding them into the op amp. And what you're getting essentially here is two different gains. Your V2 is given by the gain shown there, which is in blue in the top blue box, G2. And that's the gain coming from the V2 section, which is the bottom part of the op amp going into the non-inverting side. And then you're also going to get this inverting op amp, inverting gain coming from G1 and from the first signal. And if you write this all out, and I'll give you some time to be able to look at this, you can pause the video and work through the math on your own. But essentially what that negative is doing for the difference amplifier is subtracting one signal from the other. So if you look in the bottom right in that kind of bluish box, you see the blue arrow pointing to the negative sign. That's what the difference is doing. You have the first gain, and that's times your V2, which is your second signal, minus your gain that is shown by the V1. And so you're subtracting one from the other. That's why it's called a difference amplifier. You're taking two signals and you're subtracting one from the other. Voltage follower or buffer circuits, again, buffer sections of the circuits, these are really kind of handy. Voltage followers have a gain of 1, so they don't amplify at all, but they do buffer a circuit or protect it. And this means that you're essentially, it helps prevent electrical problems or noise or whatnot coming in more complex circuits. So if you ever have a doubt about it, I put a buffer circuit in there just to be sure, and that way you have a little more protection for expensive electronics or whatnot. Here we have a quick summary slide of a couple different non-inverting, inverting summing, subtracting, voltage follower buffer, and then non-inverting summing. And these are the basic op amps that we're going to use. Essentially, in mathematical terms, this gives us our positive, our negative number, our positive number, our addition, and our subtraction. In this example, this is for 5. We have an elevation sensor. So this is a very interesting example as well. So this shows how to use a sensor with an op amp in order to boost the sensitivity so that you can do something with that data coming out of the sensor. So some sensors have very, very small, actually most sensors have very, very small voltage changes just because they're small sensors, they're MEMS devices, microelectrical mechanical system devices, or whatnot, and they don't really change the voltage very much. Maybe they just change it from 0 to 0.1, and it's the values in there. So we use an op amp to be able to change that 0 to 0.1 to 0 to 10, because we can do something with 0 to 10. That'll turn on LEDs, that'll turn on music or whatnot. So this one is kind of going through the sensor response, and you have an equation here for what your sensor response is, and you have an equation for your desired output. And this is kind of walking you through a system of being able to design an elevation sensor. And again, this one's in the book. You can ask me more and we can go through this in person. I think with the project that we're going to do in class that this is going to be really well taken care of. So I'm going to leave this one here until further notice. Example 4.6 here, we have multiple op-amp circuits. So the whole purpose of this example is trying to show that you can string many, many op-amps together in order to to create more and more complex equations. And so the more op amps you string, the more you can tune a design, the more you can do amplification and then compare something and then maybe have a comparator at the end to make something turn on and off or LEDs turn on and off. It depends on what your electrical design is, but the knowledge that is important from this side is that you want op amps that you can string op amps together to make much more complex circuits, and there's no limit really to how many op amps you can string together. In this one, another thing for op amps useful for is in order to improve measurement uncertainty. So let's just say I have a temperature sensor and it's a direct measurement. So I'm plugging that sensor in and I'm reading the value exactly off. So if it's a temperature sensor, it'll have a resistance. And based on that resistance, I'm going to get a voltage coming out through my multimeter, and that voltage is going to tell me how hot or cold it is. So thermistors, which are a temperature sensor, thermal resistors, or a resistor that changes resistance based upon the temperature, have an accuracy of like 1 or plus or minus 1%. So plus or minus 1% on 21 degrees equals 0.21 degrees Celsius, which is actually for a lot of things too much. So a lot of my research in artificial skin and whatnot, I need very, very specific temperatures, especially when working with hydrogels, because hydrogels have melting points at like 30.02 degrees Celsius. So I need to be very close to that melting point and not go over or not go under if I'm trying to keep it liquid. So a differential measurement, though, using an op amp, a differential op amp, allows you to use the exact same thermistor, but you can shift your percentage of error. And here you're getting 0.01 degrees Celsius. And that's a really, really useful thing to do because you're getting a much, much cleaner and more accurate temperature sensor, even though you're using the exact same electrical thermistor. The only difference is you're using an op amp to be able to compare it to a fixed reference temperature like 20 degrees Celsius. So this is a very important way of doing more accurate signals. So in your projects or whatnot, if you find that your signals are extremely inaccurate and you're trying to get like maybe it's 15% plus or minus and you need it lower, op amps are a great way to be able to remove that, especially using the differential measurement features of a differential op amp. Another important op amp that we have here is called the instrumentation amplifier. This is a really cool kind of generic op amp. So what this does is these first two op amps take two different signals in, and you have this potentiometer or variable resistor R2, which usually is a knob that you can turn, and that can tune your circuit to have it exactly how you want. And then the last op amp there is essentially your adds the two different signals together and amplifies either one or the other at a given rate. So that's a really cool op amp. YouTube instrumentation amplifiers, these are very useful. I'm presuming a few of you will use them in your projects. The benefit this has is that gain control, that R2 there, potentiometer. That allows you to manually tune it. So if you're trying to listen to an op amp and you want it to sound something specific, having some kind of user-defined feedback or gain control allows you to tune which percentage of op amp 1 to op amp 2 you want. And that can be very important. So op amps are also used in digital and analog converters, and what this does is they convert digital values into analog values. And so your MyDAC or DAC is data acquisition. So that's essentially data analog converter, digital analog converter, DAC. And so what this is saying is it's taking an analog value, so any value between 0 to whatever you're testing, 0 to 1, let's say. So that includes 0.01, 0.0001, 0.0001, and it's making that into a very set number. And this is how computers take and break signals down, because analog signals have infinite amount of points in them. Digital signals do not. Digital signals have a fixed amount of points. And so this is how your DAC or your MyDAC takes a signal which has an infinite amount of points and breaks it up into something digital which has a number behind it. And this is a really, really cool circuit. And the digital, the 4-bit example here, the 4-digit example, showing you how you get to 15 volts. Because remember, your MyDAC goes up to 15. So that makes it have 8 digits. And these are half the digits, 0 to 111111. and the values that are assigned to them. So inside a digital analog converter, you have a whole bunch of these essentially little switches, and as you're increasing your voltage, these are going to switch on and off. And switching them on and off is going to amplify your signal to be louder and louder. And that's essentially how you can make a digital to analog converter. And the math behind these is pretty cool. They're very useful circuits. Usually, we'll buy them and purchase them because you can get like a 24-bit analog digital converter or something much bigger. But in a pinch, you can always make one with an op amp too, if you need that kind of signal, and you can go with low resolution signal processing. So this is something I highly encourage you to look up on YouTube. Just Google search digital to analog converter and see what comes up on YouTube, and try to learn about building one with an op amp if you need it. So, in summary, these are the most important parts from this chapter. We have ideal op amps, we have non-inverting op amps, we have inverting op amps, summing amps, difference amps, we have voltage followers or buffer circuits. We have an instrumentation amplifier, which has a gain control resistor, which is the potentiometer in it. And then we also have MOSFETs, which I'm going to talk about actually in a little bit more in class. And we're going to talk about that because those are field effect transistors. And they kind of do a similar thing for amplification, but they have some different properties. And essentially, MOSFETs allow you to boost things current up more than an op amp. So op amps allow you to put a little bit of current out, maybe 10 milliamps. And MOSFETs, there's MOSFETs that let you put out like 10 amps of current. And those are the ones that you use to like melt metal, or you can do a whole bunch of different things with those. But MOSFETs generally come in line with op amps and circuits, so we want to look at them a little bit more in detail. So we'll do that soon. But for now, this is your basis of study for the chapter in op amps. Have fun, guys.